equation of motion, right? Okay, so let's just quickly summarize what we did. What we were saying that any physical system, as long as you can identify a single coordinate or independent degree of freedom that can describe the motion, can be modeled as a single degree of freedom system, right? And for the timing, you just accept that. We'll demonstrate later how we can do that modeling. But with that said, we said that if any system can be assumed, if it is moving only in one direction, can be assumed that basically consists of a single degree of freedom system. The mass, which is what is moving, whether translational or rotational, doesn't matter, its motion is basically resisted by two elements. We call one of them as a stiffness element, and the other one, which is just by definition, not by derivation, because it's much more complicated than that, we call that the damping element. Okay? So if this is subjected to an external force, this is going to move like this, and then we just simply use the lumbar principle. The lumbar principle, which says you can basically set up the free body diagram of a dynamic system by including a fictitious force, which we call inertial force, force of inertia. So if it's linear direction, it would be mu double dot. If it is rotational, it would be mass moment of inertia times the rotational acceleration, right? So it would be this. So if we just write set up the free body diagram, here we have a linear force which is proportional to the displacement, or if we have that, the stiffness, which we will talk about that, would be just K times U. This, by definition, we say it's C, damping coefficient times the velocity, is not based on any kind of physical derivation, based on assumption. And then, of course, the applied force, and we set up from this free body diagram this equation of motion, right? So that's where we work. And as I said, of course, this equation has everything we need to know, has information about the system. In other words, these elements are the inherent characteristics of a physical system. It's better called this equivalent stiffness. This we call that equivalent damping. And this is equivalent mass of the system. And this is the disturbance, or the external, I call that disturbance. Can be a time-dependent force, displacement, and whatnot. So this is what we call equation of motion. So, as I said last time, now studying the vibration, of course, first of all, we would restrict our study to a single degree of freedom system, and studying the vibration, okay, consists of basically two important areas. So first, we need to know how to set up this single degree of freedom system model. In other words, so far, you have only accepted from me that any system in the world can be thought of having just a mass, a stiffness, and damping element. But how do you, given a physical system, how do you come up with those quantities or those parameters? So that requires to show how different physical systems can be modeled to be just a single degree of freedom system. So we will spend some time doing that. And the second, of course, solving the equation of motion. So based on the system itself and the type of forcing function that we have, these are the categories or areas that we will be studying. So we will look at these cases. First, we make two major assumptions. One is that first we assume in that modeling part, as we set up the equation of motion, as we define the system and so on, the physical system has no energy absorption capability. It only consists of a system that can resist deformation, and that's it. In fact, in strength material, that's all you did. You are not dealing with any damping. You have a force and causes deformation, except that here the force is time dependent and this displacement is time dependent. So case one then, we assume C is equal to 0, and we call that an undamped system. Okay? Case 2, C is not equal to 0. So we call that a damped system. So we look at both cases, and both basically situations that we need to set up the equation of motion. Then, depending on what we have on the right-hand side, also we have different categories. I briefly talked about that last time. So as far as the forcing function, okay, case 1 is when forcing function is 0, and case 2, forcing function is not 0. In other words, case 1 is when something has been disturbed already, as it started oscillating, then the force is gone. The source of vibration is gone, but obviously the system continues to move or continues to vibrate. But in each of these cases, we can have either of these two. So we can have an undamped free vibration. So we call this free vibration because the system is not subjected to any force, so it's vibrating freely. Or we have undamped forced vibration. Same thing here. We can have damped. Oh, I'm sorry. In fact, the way I categorized it was different. We can have undamped. I should have looked at only at the case. Maybe, in fact, you know what? I did it actually in the other class. I did it differently, and I'm going to do it the same way because it would be better. In case of the, let's look at it this way. In case of the undamped, okay, case, we can have, okay, either a free vibration, that is, Ft is 0, or we can have force vibration, where Ft is not equal to 0, okay? And in the case that Ft is not equal to 0, obviously, we look at a few possibilities. We look at a harmonic input, we look at a periodic oscillation, and we look at a general forcing, like impact, blast, and so on. we do the same for the case of damped vibration. So we look at, again, as free vibration when f of t is equal to 0, or we look at the force vibration, and again, we look at these three cases. So these are all the cases we are going to study. We look at the undamped case first, and then the damped case. So to begin with, as I said, we are going to focus on this. However, in order to focus on that, first we need to define some of the important characteristics or parameters that are very important in mechanical vibration, and in fact, that is the foundation before doing this. So what I will do, if I can number these so that would be a little bit more meaningful. This is case 1, right? And this is case 2. So if I call this maybe 1A, this becomes 1B, and of course then this becomes 1B1, 1B2, and 1B3. We are going to study all of these, right? So this becomes 2A, and this becomes 2B, and so on. So 2B1, 2B2, 2B3. So we study all of these. 1, 2, 1A, 1, so on, so on, so on. So to begin with, this is what we will do. Let's focus on the case of undamped free vibration. And the reason for that is we want to find some more specific information about our system. There are some important inherent characteristics that by looking at the free vibration of an undamped system, we will discover. And that would be, in fact, one of the most important physical parameters or characteristics that we will be dealing with the rest of our lives, okay? So let's just start with free undamped vibration, okay? So if the system has no damping, in other words, just consists of a stiffness element and a mass, okay? Or it can be, of course, a rotational system, doesn't matter. The equation of motion would be very simple. So this is what would be a special case. You remember from differential equation how you solve this, right? You just set up the characteristic equation, okay, which would be m lambda squared plus k is equal to 0. And you find the roots of this characteristic equation, which would be lambda 1 and 2, which would be plus and minus I times k over m. Okay? And then there are two, depending on how many roots your characteristic equation has, there would be as many solutions to this equation. So you have U1 and U2, okay? U1 and U2 are, if you remember from the differential equation, would be this, and this would be the other one, okay? Or in general, it would be like this. So the total solution would be sum of these two. In other words, you have C1 e to the I k over m t, oops, I dropped the t, which is the most important part, right? Plus C2 e to the negative I k over m t. Now, you remember from Mr. Euler, right? A complex number variable can be written in so many different forms. One was this one, the other one was in the polar coordinates, so you wrote it as r cosine theta plus I sine theta, and another form was e to the I theta, or r times e to the I theta. So, therefore, we will write these in this form, or they are in this form, but we will write them in terms of the alternative form that they have. In other words, since e to the I theta is the same as cosine theta plus I sine theta, so we will just convert these to that, this solution to that form. So u would be C1, okay, times cosine of k over m t plus I sine k over m t plus C2 times cosine k over m t minus I sine k over m t. So that is the solution. We can further simplify that. If you factor out the common terms, this would take the form C1 plus C2 times cosine of k over m t plus C1 minus C2 times, of course, I sine k over m t, right? Nevertheless, I mean, these two are just simply constant. So let's make the life easier for us. I just call this A1 cosine of k over m t plus A2 sine of k over m t. So the displacement response of a freely vibrating system is a harmonic, a sinusoidal function. And the frequency of that harmonic oscillation, interestingly enough, is what? If I call that this, the frequency of that oscillation, only depends on the inherent or the natural characteristics of the system. The natural or inherent properties or the characteristics of the system are what we have discussed: the stiffness and the mass. We're ignoring, of course, the damping, right? So the natural frequency is only a function of the stiffness and the mass of the system. Since this is only depends on these natural inherent characteristics, we call this natural frequency. So as you can see then, every system in the world has its own unique natural frequency, because every system has a different stiffness capability and has a different inertia. So every system in the world has its own unique natural frequency. This is probably the most important concept in understanding mechanical vibration, because this is a property or inherent characteristic that really defines any system. It's almost like the ID card of any physical system in the world. So every system in the world has its own ID card, which is its natural frequency, if I can think of a sort of an analogy. We'll beat that to death as far as understanding it. So let's leave that for the time being. at least if nothing else, for the time being, you can write this in a simpler way. I write it as A1 cosine omega n t plus A2 sine omega n t. So this is the general solution of this differential equation. In order to solve for these two parameters, which are constant of the in this solution, you have two constants, so you need two initial conditions to solve for them. So you remember again from the differential equation, let's say you have the value, or you have the value of the displacement and response at certain time. Make it easier at time 0. So let's say at time 0, the displacement at time 0, that's the notation, right, is some value. And I show that as u sub 0 with this bar. It means a specific numerical value. And velocity at time 0 also has certain value that I call that u dot naught bar. U bar dot naught. Okay. All right. So all you need to do, just substitute these into that equation to find A1 and A2. So you can see that if I substitute t equal to 0, this becomes 1, right? And this goes to 0, right? So, and this is of course u0. So therefore, A1 would be just u bar naught. And if you take the derivative of this, which would be the derivative, maybe I do that quickly. So if you take the derivative at time t, right, you have negative omega n A1 sine omega n t plus omega n A2 cosine omega n t. Now if you set again time equal to 0, you have u dot naught, right, which is velocity at time is equal to 0. You substitute for t again to be 0, so this goes to 0. This is 1, so you have omega n A2. So that means A2 then is u dot naught over omega n, right? So you just substitute that into that equation. So in terms of the initial conditions, if the initial conditions are given, that would be cosine omega n t plus u dot bar naught omega n sine omega n t. So this is in general terms, this is in terms of some initial conditions. Any questions? So you can easily see the response of a freely vibrating undamped system then is just a simple harmonic function, right? We can actually further simplify this so that you can see that even easier or more visibly how this is a simple sinusoidal function. How do I do that? Let me start from here. What I will do, okay, I have u, I drop t just for, I guess, being easier, but you know u is a function of time. So if this is A1 cosine omega nt plus A2 sine omega nt, I can simply multiply this by a quantity like this, and divide it by that. So you would say, am I crazy doing that? Why do I do that? Because I haven't done anything. I mean, this equation hasn't changed because I've just multiplied it by unity, right? But the beauty of it is that if you look at these two quantities now, or these two factors, if I call this alpha, this beta, right? Alpha squared plus beta squared is 1, right? And there are only two functions in the world that if you square them and add them up, their sum is equal to 1, and that is sine and cosine, right? And these are, of course, numerical values. You saw that they depend on only on the initial condition. So I can say that alpha is sine of some angle, and beta is the cosine of some angle. So therefore, now you have sine theta cosine omega t, you have cosine theta sine omega t, right? And let me call this just is going to be a constant. I call it A, right? We can find it, but let's call it A. So sine, cosine, cosine, sine. You remember that from trigonometry? U of t then becomes A times sine of omega n t plus theta. Sine alpha, cosine beta, sine alpha is sine of alpha plus beta, right? So that's what it is. So this is the same equation as this one, except that it's written in a single sinusoidal form. The beauty of it is that now you can more easier understand this and study it, okay? So how? Let's plot that. If you plot that function, in other words, you plot u of t, okay? And I will do that, I can do that in terms of, in fact, the those initial values, because if you now substitute also these in here, you can see that if you, in terms of those initial conditions, you end up with something like this. Basically, you end up with the A becoming, all you need to do is just substitute those, do some algebra. You would be A would become u dot squared plus u dot naught over omega n squared, and theta is the arc tangent of u dot omega n over u dot naught. Okay. So if you want to establish that in terms of the initial conditions. Now, if you plot this u, it would look something like this. As a function of omega, I would plot it as a function of omega n t. This is going to look like this. So let's see. So it is a sinusoidal function, okay? That is peak to peak is 2 pi. This is basically pi. So this is, in other words, this is 180 degrees, this is 90 degrees, okay? So that's how you basically plot that. And so this is u of t. You can do that, of course, much more accurately and quickly than I do that here. But so in this curve, at u, at a time is equal to 0, which is represented by this line, right? That's the time is equal to 0. this is the initial velocity, the slope of the curve, it represents the initial velocity, and this is the initial displacement.
So the x-axis is omega and t.
Omega and t, right. You can plot as t, but I just do that in terms of omega and t, so it's easier. Okay? Theta is what we call a phase angle. Okay? In other words, it shows how this signal lags behind a sinusoidal function, pure sinusoidal, say sine of omega t, right? How much it lags behind that, right? There is something else. There are many observations actually you can make. We don't get into details of that, and there are all kinds of fun discussions you can read in the book. If you now plot the, say, the velocity curve. Velocity is a derivative of that, right? So it would be what? It would be negative omega n, I'm sorry, omega n, a cosine omega n plus theta, right? So there's the derivative of this function. In other words, when this is 0, this would be maximum. When it is maximum, this function will be 0. So would be something like this. So would be something like this. Okay. So it's just, because when sine is 0, cosine is, 1 and so on. So that's the displacement. Correct. So this is your, okay, this is the initial velocity. But the beauty of it is, now if you look at it, what it means is when, say, when displacement is 0, okay, velocity is maximum, right? And for the velocity, it takes 90, in other words, omega n t is equal to 90 degrees, or pi over 2, doesn't matter. And of course, you can find that. So it takes a value of time of 90 degrees, or pi over 2, maybe I will write it as pi over 2, pi over 2 omega n, okay, to reach as 0 value. So when the velocity is 0, I'm sorry, the displacement is 0, velocity is maximum, but after a time of t over 2 omega n, after the displacement is 0, velocity goes to 0, right? So that means basically how the velocity and the displacement, and you can also plot the acceleration and relate these two and so on. We'll do that. You do all kinds of stuff in the lab to study signals and so on. But for the time being, we are just going to focus on the fundamental concept that is very important to almost beat that to death, and that is this creature omega n, which is the natural frequency. Okay. As I said, this quantity is really what defines, or is the ID card for any physical, whether it's mechanical or structural system. So let me just summarize, by emphasizing on that, summarize what we have done so far, okay? So first of all, we said that the motion or the response of a single degree of freedom undamped system is basically harmonic. That means it repeats itself, okay, cyclically, right, at any time t plus 2 pi over omega n. Okay, that's, so the period, in other words, of this system, that's the frequency. The period is what? 2 pi over omega n. That is the time at every which of these, this interval, this motion repeats itself, right? So this is one period, one period, one period, one period, okay? So it repeats itself. That's observation number one. Observation number two, or not observation, information or conclusion number two, that I will write it down. This frequency of this system, which we call the natural frequency, is this. In this form, this is the unit for is radians per second. You can convert this to another unit, okay, by dividing this value by 2 pi, and we call that hertz. So hertz is a non-dimensionalized, basically, form of the natural frequency. And there's a yet, now we are going to start focusing on this, because as I said, and I promised, next couple of weeks, now that we have just derived the equation of motion, next couple of weeks, we're going to focus on understanding how to set up that model. In order to do that, let's pay more attention to this fundamental quantity, which is really the basis for understanding the system. So I'm going to write this natural frequency, which is this relationship, this way, K over M. But what is M? You typically, normally you have the weight of the system, right? So let's write this in terms of the weight instead of mass. And what is weight? What is mass? Mass is weight over the gravitational acceleration, right? So I can write this that way, and instead what I will do, I will write that in terms of hertz that way. So the natural frequency of a system then is 1 over 2 pi times K times G over W, right? If you're dealing, of course, with wonderful British units, right? This is 32.2 times 12 per second, right? Meter per second. And then, therefore, I can write this, if I substitute for that number, 1 over 2 pi times G over K. Now look at this way. I'm going to look at it again differently. What is K over W? Assuming that the system is only moving in one direction, remember? In other words, you have something like this, right? That moving in one direction, oscillating in one direction, and this is the weight, okay? W over K is what? Is the displacement of the system, static displacement under its own weight, right? W over K, right? W is K times this, right? The only force statically acting on a system that is not vibrating, just basically under static law, its own weight, is the static deformation, right? So instead of W over K, you can say this is the displacement of the system under its own weight. So why don't I do that? I will write it that way, and then I will have G over static displacement. So if you write it this way, I can now write it G, square root of G over 2 pi, okay, times 1 over the square root of delta st. If you put this value in there and simplify that, approximately, you see this would be almost 3.14 happens. That whole thing becomes 3.14, which is equal to almost pi. So the natural frequency of a system, any system, can be measured, in fact, by knowing the static equilibrium of the system. What is sounds like kind of complicated, but what does that mean? I remember, in fact, one case many years ago, that there was a company, offshore oil platform company, they wanted to design something, and then they had approached some consultant, including myself. And all they wanted was just wanted to know some basic dynamic characteristics of this platform, because it was being built in basically an environment, you know, basically the ocean waves and whatnot. You wanted to make sure that frequency of the forcing function that causing basically the motion of this is way away from the natural frequency, because we will see that. One of the important things about natural frequency is that what it means, if you have a forced vibration and the frequency of the forcing function becomes very close or equal to the natural frequency of the system, the response of the system just goes to infinity, or the system just basically would collapse, because amplitude increases and increases and increases. We'll talk about that, which is called resonant phenomenon. So these guys wanted to find out if it is adequate to assume that the natural frequency of this offshore platform is way away from the forcing function frequency. So this guy, they had approached, offered them a very heavy price tag to perform a finite element analysis of this wonderful offshore platform, because it's a very complicated stuff, so you need to set up a finite element analysis, do all kinds of things. But then I said, you know, I'm going to charge you peanuts, because you look at this, it's almost like a cantilever beam, right? So if you know what the stiffness of this column is, which is not difficult, I mean, you can find out, I mean, you have had strength of material, 3I over L cubed, that's what it is. You have to have modulus of elasticity, moment of inertia, and that's it, right? But you know what that is, and this is basically a long mass, so you have the mass of this creature, whatever heavy it is, doesn't matter. So if you find its weight, and let's say you do not want this, okay, to go more than, say, 20, to be more than, let's say, 20 centimeter in motion, right? In other words, if you assume that the static displacement of this beam is only 20 centimeter, right? Just substitute it here, you find the natural frequency, that's it. You don't have to do sophisticated analysis. So that's one of the beauties of this relationship, that if you're given any system, forget about vibration, forget about dynamics, as long as you know what is the weight of that system, right? And you know the stiffness of the system is a beam. And you just divide the weight by the stiffness, you get a value, and just put in here, you find the natural frequency, okay? So with that said, we'll start talking about modeling the system next time.